This lesson deals with supplemental problem 15.1. You can find this problem in the ECE202 ebook in the chapter 15 supplemental problem starting on page 1. Given two coupled coils with a mutual inductance, can you show that the product of L1 and L2 is always greater than or equal to the mutual inductance squared? And let's do this by calculating the total energy stored in the inductances L1 and L2. Now we have a set of formulas for voltage, a set of coupled coils, and that is that V1 is equal to L1 di1 dt plus or minus m di2 dt. We find the power absorbed by the first coil, that would be the product of its voltage times the current. So multiply each term here by I1. Likewise for the second coil, the voltage across it is equal to plus or minus m di1 dt plus L2 di2 dt. Let's multiply that by the current flowing in coil 2. Now give me the power absorbed. So let's multiply each term by I2. And then the total power is adding those together. Now let's pull all the things that multiply L1 together. So I've got this term here. Now for m, or plus or minus m, I've got this term, which is here. And I've also got this term, which is also over here. And then pull out the L2, and I got a I2 of t times di2 of t. Now if I could express this equation for power in terms of a derivative, then that would be the energy. Let's take a look at this. Take the derivative of I1 squared. That would be equal to 2 times I1 of t raised to the 2 minus 1 power times the derivative of I1 of t. And that's just going to be equal to 2I1 of t di1 of t dt. And that looks like this term here multiplied by 2. Take the derivative of I1 times I2. By the product rule, we'd have first term times the derivative of the second term plus the second term times the derivative of the first. Let's go back and look at this expression now. So here's this term here. I'll bring the 2 on the other side of the equation. So we have a 1/2 times L1, and that would be then the value of I1 squared. This term here looks exactly like this term, except there's a plus and minus m in front. And then we also have a similar expression here for I2 of t. The same thing, I'd use this by putting a 2 subscript on here. So bring the half over here, so I have a 1/2 L, and then that derivative would then be the value of I1 squared. Okay, so what's in the brackets here then would be the total energy absorbed, because its derivative would be P of t. So my total energy then is equal to this. By the conservation of energy, I know this is always greater than or equal to 0, because the inductances can't generate energy, they can only store it. Now suppose that I2 of t is 0. You have nothing going into the secondaries of a transformer. Well then from this equation, the term 1/2 L1 I1 squared would be greater than or equal to 0. Since squaring something is always positive, that implies that L1 is always positive. Same thing with letting I1 equal 0. We would have this 0, and then squaring a term is always positive. That implies that L2 is also positive. Last possibility is that both I1 and I2 are not 0, and so we have this equation for the total energy. Let's divide through by I2 squared. So the first term then becomes 1/2 L1 times I1 of t squared divided by I2 of t squared, plus or minus m, and divide through by I2 of t squared, so I'm going to cancel one of those. So I've got I1 over I2. And then lastly up here, I'm going to divide through by I2 squared, and I just have a 1/2 L2. Let me define this as a function f of x, where x is equal to the quantity I1 over I2. So I would have 1/2 L1 times the ratio of I1 to I2 squared, or minus m, ratio of I1 to I2, and then just a constant here of 1/2 L2. Now again, this has to all be greater than or equal to 0. Let's use a second derivative test to find the smallest value of this quantity, which again still has to be positive. So we'll take the first derivative, set it equal to 0, and find the critical points, and then take the second derivative, and then see what the sign of the second derivative is. If it's greater than 0, it's a relative minimum, less than 0, a maximum, and equal to 0, a point of inflection. The derivative of this, we're going to have 2 times x of t times the scalar 1/2 L1, plus or minus m times just 1, and then plus 0. The 2 and the half cancel, and I just get L1 xt plus or minus m. So setting that equal to 0, we can then solve for the x of t, which we'll call x critical. That's going to be equal to plus or minus m. On the other side of the equation becomes minus over plus m divided by L1. Second derivative with respect to x of t is just going to be L1. We already argued that L1 is positive. So we have a relative minimum. Our quantity is always positive. The minimum value, we've got an interesting result here. So let's go back and plug this back into our equation. So we have 1/2 L1. I've got x squared, which is now minus over plus m over L1, quantity squared, plus or minus m times x of t plus 1/2 L2. Now when you square this, the sign is always positive, because we have 2 minus signs or 2 plus signs. Likewise over here, the product of this times this and this times this is always negative. And then what I've got here with the L1 and the L1 squared is cancel that. So I've got 1/2 m squared over L1 minus m squared over L1. So I'm going to get a minus 1/2 m squared over L1. But then likewise, I've got here a 1/2 and then an L2. So I can find a common denominator. So I got L1 minus m squared and then L1 times L2. This has to be greater than or equal to 0. That implies that L1 times L2 is greater than or equal to m squared. And this is supplemental problem 15.1.